Welcome back to the deep dive. Today we are tackling, well, a really huge topic in physical chemistry. The world of molecular interactions, the forces that basically hold everything together.
Yeah, our mission here is to connect the dots. Starting from the tiny electronic structure of a single molecule, how its electrons and charges are arranged, and scaling all the way up to the big macroscopic properties we see. Things like liquids, polymers, even how biological molecules manage to assemble themselves.
It really is a fascinating journey. We're essentially looking at how the electrical character of molecules dictates almost everything about condensed matter, from simple liquids right up to the function of DNA. We've got about 5 main areas we need to unpack today.
Okay.
And we really have to start at the absolute foundation, electricity, but at the molecular scale.
Right, let's dive in then. Topic 14A, I believe. And this kicks off with two absolutely key concepts for understanding a molecule's electric personality. Its permanent electric dipole moment and its ability to be distorted, which is polarizability. Exactly. So, the electric dipole moment, usually written as mood nu, think of it like a permanent imbalance of charge within the molecule. It happens in polar molecules because atoms don't share electrons equally. You get a slight positive charge in one place, a slight negative somewhere else, separated by a distance r.
So nu mut equals QR dollar, charge times separation.
That's the one. Nu mut equals QR dollar. It's often measured in a unit called the dB, symbol D. And even though the values might seem small, this permanent charge separation is, well, it's the starting point for so many intermolecular effects.
And it's not just about having polar bonds, is it? The overall shape, the molecular symmetry is critical.
Oh, absolutely crucial. You can have very polar bonds, like in carbon dioxide, tech CO2. But because tech CO2 is perfectly linear and symmetrical, those bond dipoles point in opposite directions, and they just completely cancel out. Net result, nonpolar molecule.
But then you take ozone, text O3.
Right, ozone. It's made only of oxygen atoms, so you might think it's nonpolar. But it's angular, it's bent. Because it's bent, the bond dipoles don't cancel. They add up vectorially, giving the molecule an overall dipole moment. So yeah, symmetry is absolutely key.
Okay, that covers the permanent dipoles. But then there's this other property, polarizability, symbol alpha. Alpha. This sounds different. It's about being induced.
Yes, exactly. Polarizability is the molecule's capacity, its willingness really to have its own electron cloud distorted by an external electric field. Think of the electron cloud as a bit flexible. When a field comes along, it can push the electron slightly to one side, inducing a temporary dipole moment.
Temporary, right. So it only exists while the field is there.
Precisely.
Right.
And we quantify this flexibility using something called the polarizability volume, often written to alpha prime. And here's where it gets really interesting, connecting back to quantum mechanics. This alpha value, this measure of flexibility, it turns out it's strongly related to the molecule's electronic structure. Specifically, it correlates inversely with the energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, the HOMO-LUMO gap.
Okay, hang on. Inversely. So if the HOMO-LUMO gap is small,
then the molecule is highly polarizable. A small gap means it takes very little energy to excite or shift the electrons around. You can think of its electron cloud as being, well, kind of floppy or easily distorted, highly malleable.
Got it. And this inherent floppiness then determines how a whole bunch of molecules, a bulk material, responds to an electric field, polarization.
That's exactly where it leads. The polarization of a bulk material, how much it responds, depends critically on the frequency of the applied electric field. How fast is it oscillating?
Right, because the molecules have to physically respond.
They do, and different responses have different speeds. If you apply a field, the permanent dipoles try to rotate and align, orientation polarization. But if the field starts oscillating really fast, say at microwave frequencies around 10 hertz, the molecules just can't rotate back and forth quickly enough. That contribution is lost.
Okay, so orientation drops out first. What next?
Then, as the frequency increases further into the infrared range, even the faster process of distorting the molecule's shape by slightly moving the nuclei, distortion polarization, can't keep up. That drops out too.
So at really high frequencies, like visible light.
The only thing left that can respond almost instantaneously is the electron cloud itself just shifting slightly, electronic polarizability. So the material's overall response changes dramatically depending on the frequency of light or fields you're using.
That's a great bridge from single molecules to bulk properties. Okay, let's build on that. Segment 2. How do these electric properties actually lead to interactions between molecules? This is topic 14b, right? The forces that hold things together.
Exactly. The fundamental idea is pretty simple. Attraction leads to cohesion, molecules sticking together, while repulsion stops them from collapsing into each other.
And a lot of the attractive forces get lumped under the term van der Waals interactions.
That's right. It's a bit of an umbrella term, but a key characteristic, a signature you should look for, is how the potential energy of these interactions depends on the distance between molecules. Typically, it's proportional to 1 over r to the 6th power. Van propto 1r to the 6th.
1 over r to the 6th? Why that specific dependence?
It emerges naturally from the interactions involving dipoles and induced dipoles. It's a relatively short-range force compared to, say, the 1 over r dependence of a simple ion-ion interaction, but it's long-range enough to be effective in liquids and solids. It falls off reasonably quickly, but not too quickly.
Okay, so what types fall under this 166 category?
Well, first, there's the interaction between two rotating permanent dipoles, like in a liquid. This is sometimes called the Keesom interaction. Because the dipoles are tumbling around, the interaction averages out. But there's a slight preference for attractive orientations, leading to that 162 dependence. It also depends on temperature, inversely proportional to T, because thermal energy disrupts the alignment.
Makes sense. Lower temperature, better alignment, stronger average attraction.
Exactly. Then there's the dipole-induced dipole interaction. Here, a molecule with a permanent dipole comes near a neighbor that might be nonpolar but is polarizable. The permanent dipole induces a temporary dipole in the neighbor, and they attract. Again, this interaction mechanism leads to a Van-der-Propto RR66 dependence.
Okay, and the last one, the one that's always there.
Ah, yes. The London dispersion force, sometimes it's called dispersion force. This one is universal. It exists between all molecules, even perfectly nonpolar ones like argon atoms or methane molecules.
How does that work if there's no permanent dipole?
It's down to quantum fluctuations. Even in a nonpolar molecule, the electrons are constantly moving. At any given instant, the electron distribution might be slightly uneven, creating a fleeting instantaneous dipole. This tiny temporary dipole can then induce a corresponding temporary dipole in a neighboring molecule.
Ah, so it's an induced dipole effect.
Precisely.
Yeah.
And because it arises from these correlated fluctuations, the resulting attraction also follows that characteristic Van-der-Propto 1r66 relationship. And importantly, because it's always present and additive over many atoms and large molecules, it often becomes the dominant attractive force, especially for nonpolar substances.
We have to pause here, though, and mention the special case, the hydrogen bond. It's much stronger, right?
Oh, significantly stronger. Typically around 20 kilojoules per mole, which is, roughly 10 times stronger than a typical van der Waals interaction. It's a very specific interaction, usually denoted as AHB, where A and B are highly electronegative atoms, most commonly nitrogen, oxygen, or fluorine, and H is the hydrogen atom bonded to A.
And we know it's special because...
Well, experimentally, the distance between A and B in a hydrogen bond is considerably shorter than what you'd predict just by adding up their van der Waals radii. There's a real directional strong attraction there. You can think of it partly electrostatically, but a fuller picture involves molecular orbitals too. It's crucial for the structure of water, proteins, DNA life, basically.
Okay, so we have all these attractions pulling molecules together, but they can't collapse completely. There must be repulsion too.
Absolutely. As molecules get very close, their electron clouds start to overlap, and the nuclei start to repel each other. This repulsion increases very steeply at short distances, much faster than the 166 attraction falls off.
So how do we model the total interaction, the balance between attraction at longer distances and repulsion at very short distances?
A very common and useful approximation is the Lennard-Jones potential, often called the 12-6 potential. It combines the attractive 166 term, multiplied by a negative constant, with a repulsive term that goes as $1.12, multiplied by a positive constant. That $12 term provides the very steep repulsion at close range.
Why 12? Is there a deep reason?
It's partly chosen for mathematical convenience. It's the square of the 36-Bilder term, but it does a reasonably good job of representing that sharp increase in energy when things get too close. The beauty of the Lennard-Jones potential is it gives us two key parameters for any pair of molecules. The depth of the potential, well, epsilon, which tells us how strong the attraction is at its maximum, and the distance, $, where the potential energy crosses zero, sort of the effective contact distance.
Okay, that gives us a good model for pairs of molecules. Now let's scale up again. Segment 3. What happens when we have trillions of these interacting molecules together in liquids? Topic 14C.
Right, liquids. They're fascinating because they're sort of halfway between the perfect order of a crystal and the total chaos of a gas. They have structure, but it's local and transient.
How do we describe that structure?
The key tool is the radial distribution function, usually written GR/JR. If you pick one molecule as your center, GR tells you the probability of finding another molecule at a distance trom away from it, compared to just a purely random distribution.
So what does GR look like for a typical liquid?
It shows distinct peaks. There's usually a sharp first peak, indicating a shell of nearest neighbors at a fairly well-defined distance. Then maybe a smaller second peak for the next shell out. These peaks show there's definite short-range order. But as you go further out, to larger dollars, the peaks dampen out, and GR just smooths out to a value of 1.
Meaning at long distances, it's basically random.
Exactly. Long-range order is lost. The structure doesn't persist over large distances like it does in a crystal.
And how do researchers figure out these GR functions? You can't just take a picture, can you?
Not easily. They're typically calculated using computer simulations. Two main techniques are Monte Carlo methods, which sort of randomly try out different molecular arrangements and accept them based on their energy, and molecular dynamics.
Molecular dynamics sounds like it follows the motion.
It does. MD simulations calculate the actual trajectories of all the particles over time, based on the forces between them, often using that Lennard-Jones potential we just discussed. You basically simulate a tiny box of the liquid evolving step by step, according to Newton's laws.
Okay. Now, these cohesive forces holding the liquid together must also lead to surface effects, right?
Absolutely. Think about a molecule deep inside the bulk liquid. It's being pulled equally in all directions by its neighbors. But a molecule at the surface, it only has neighbors below and to the sides. There's a net inward pull.
Causing the surface to try and shrink.
Precisely. The liquid spontaneously minimizes its surface area to minimize its energy. This tendency is quantified by the surface tension, symbol, gamma. It's defined as the work needed to increase the surface area by a certain amount. It's why small droplets naturally pull themselves into spheres the shape with the minimum surface area for a given volume.
And the surface tension in curved surfaces leads to pressure differences. I think that's the Laplace equation.
Yes, the Laplace equation tells us that the pressure inside a curved surface, like a droplet or bubble, is greater than the pressure outside. The difference is related to the surface tension and the radius of curvature, $3. For a spherical droplet, it's been out 2 gamma.
So the smaller the droplet, smaller r, the higher the internal pressure.
Exactly right. And this pressure difference is fundamental to understanding things like capillary action.
How does that work? Like water rising in a thin tube?
Okay, so if water wets the glass, meaning adhesion is strong, it forms a concave meniscus. It curves downwards at the edges. This curvature, according to Laplace, means the pressure just under the curved surface is slightly lower than the atmospheric pressure outside. This pressure difference then pulls the liquid up the tube until the weight of the raised column, the hydrostatic pressure at GNTT store, exactly balances the pressure difference due to surface tension.
Too dimmer.
That makes sense. The surface tension pulls it up, gravity pulls it down, they reach equilibrium. Precisely. And there's one more really neat consequence of this curvature effect, described by the Kelvin equation. It relates the curvature of a liquid surface to its vapor pressure.
Vapor pressure, how does curvature affect evaporation?
The Kelvin equation shows that the vapor pressure above a curved surface, like a tiny droplet, is higher than the vapor pressure above a flat surface of the same liquid at the same temperature.
Wow. So tiny droplets evaporate more easily.
Yes, they are less stable with respect to evaporation. This is hugely important. It means that for condensation to start, like forming clouds or dew, you can't just have water molecules bump into each other. A tiny initial cluster would just evaporate immediately. You need a larger surface to condense onto a nucleation center, like a dust particle or an ion. Without these, you can get supersaturated vapor.
That explains why clouds need dust. Okay, shifting gears now from simple liquids to much bigger things. Segment 4, macromolecules, topic 14D. This is polymers and biological molecules.
Right. And the first thing to grasp with many macromolecules, especially synthetic polymers, is that you rarely have a sample where all the molecules are exactly the same size. They are polydisperse, a mixture of different chain lengths.
So talking about the molar mass doesn't quite work.
It's insufficient. We need averages. Two common ones are crucial. The number average molar mass, 10 nanometers. This one basically counts the molecules. You sum the masses of all molecules and divide by the total number of molecules. It gives more weight to the smaller, more numerous chains.
Okay, number average. What's the other one?
The weight average molar mass. Here, you weight each chain length by the total mass contributed by chains of that length. So longer, heavier chains contribute more to the bar, and it's always greater than or equal to.
And the ratio between them tells us something.
Yes, the ratio bar is called the dispersity, symbol text out capital F. If all molecules were identical, monodisperse would be 1. For real polymers, it's always greater than 1. A large dispersity means a very broad distribution of chain lengths, which can significantly affect the material's properties.
Okay, average is covered. Now, structure. For proteins and such, there's this hierarchy, right? Primary, secondary.
Yes, 4 levels are usually distinguished. Primary structure is just the sequence of the monomer units, like the sequence of amino acids in a protein chain.
Just the list of building blocks.
Exactly. Secondary structure refers to the local spatial arrangement of segments of the chain. Common motifs are things like alpha helices and beta sheets, driven often by hydrogen bonding. Or parts might be just disordered, forming a random coil locally.
Then tertiary structure.
That's the overall three-dimensional shape of a single polymer chain. How the helices, sheets, and coils fold up together in space. This is determined by all those interactions we discussed: van der Waals, H-bonds, hydrophobic effects.
And finally, quaternary structure.
This applies only if the functional unit is made up of multiple polymer chains, subunits, associating together. A classic example is hemoglobin, which consists of 4 protein subunits working together.
Okay. Thinking about a single long, flexible chain, like in many synthetic polymers, what's its most likely shape if it's just floating around?
The default conformation is generally the random coil. Imagine a chain made of many links that can freely rotate relative to each other. The freely jointed chain model is a simple way to think about this. The chain just randomly folds and twists in space due to thermal motion.
How do we measure the size of such a random coil?
Well, the fully stretched out length, the contour length, is simple. It's just the number of units, n, times the length of each unit, L. So 200 equals NL. But the average end-to-end distance in a random coil is much smaller. We usually talk about the root mean square separation.
And how does that scale with chain length?
This is key. Drum scales not with n, but with the square root of n, drums of Propto N12. So doubling the chain length only increases its average size in solution by about 40%, not double. The coil becomes denser.
This random coil idea seems important for materials like rubber, elastomers.
Absolutely fundamental. Elastomers are flexible polymers, typically existing as random coils in their relaxed state. When you stretch a rubber band, you're pulling those random coils into more extended, more ordered configurations.
More ordered means less entropy.
Exactly. You're decreasing the disorder, the entropy of the polymer chains. Now, for an ideal or perfect elastomer, where internal energy changes are negligible upon stretching, the restoring force, the force pulling the rubber band back, is almost entirely entropy-driven. The system naturally wants to return to its state of maximum disorder, the random coil state.
That's wild. The snapback isn't about bond energy, it's about entropy.
For the most part, yes. And for small stretches, this entropic restoring force actually follows Hooke's law, like a simple spring.
Okay, last bit on polymers. Bulk thermal behavior. There are 2 key temperatures.
Yes, the melting temperature, 2 millars, which is relevant for crystalline or semi-crystalline polymers. It's where the ordered crystalline regions melt into a more disordered state, like any normal solid melting.
And the other one, the glass transition.
Right, the glass transition temperature, 2 millars. This is characteristic of the amorphous, non-crystalline regions of a polymer. It's not a true phase transition like melting, but rather a temperature below which the large-scale segmental motion of the polymer chains effectively freezes out. The chains become locked in place on the time scale of observation.
So below 2 or the material becomes
Rigid, brittle, glassy. Think of how plastic can become hard and shatter easily when it's very cold. That's often because it's below its $2. Above $2, the chains have enough thermal energy to move around, and the material becomes rubbery or leathery. You can often spot $2 experimentally as a change in the slope of the specific volume versus temperature curve.
fascinating. Okay, this brings us to our final segment, 14E, self-assembly. How molecules use all these forces we've discussed to spontaneously organize themselves into larger structures.
This is where it all comes together. A classic example is colloids. These are dispersions of small particles, from nanometers to micrometers, in a medium, like paint, solid and liquid, or milk, liquid and liquid. The key thing is they don't settle out quickly due to gravity.
Why not? Are they thermodynamically stable?
Actually, no. From a purely thermodynamic standpoint, the particles want to clump together, aggregate, to minimize the high surface area between the dispersed phase and the medium. Van der Waals forces are pulling them together over long ranges.
So why don't they just crash out immediately?
Because they're kinetically non-labile or kinetically stable. There's an energy barrier preventing aggregation. This barrier often comes from repulsive forces, particularly the electrical double layer that forms around charged colloidal particles in a polar solvent.
Electrical double layer? What's that?
If the particle surface has a charge, say negative, It attracts positive ions from the solution. Some bind tightly in a rigid inner layer, the stern layer, setting up what's called the zeta potential. Beyond that, there's a diffuse, mobile atmosphere of counterions that screens the particle's charge. When two particles approach, these diffuse layers start to overlap, creating a repulsive force that opposes the attractive van der Waals forces. This balance is described by DLVO theory.
So repulsion wins at intermediate distances, keeping them dispersed.
Okay. What about self-assembly in biological systems? The hydrophobic interaction seems key there. It's arguably one of the most important driving forces for protein folding and membrane formation. It refers to the tendency of nonpolar molecules or groups to cluster together when in an aqueous environment.
But it's not actually an attraction between the nonpolar groups themselves, is it?
That's the crucial, slightly counterintuitive point.
Meh.
The London dispersion forces between nonpolar groups are relatively weak. The real driving force is the entropy of the surrounding water.
How does that work?
Water molecules like to hydrogen bond with each other. When a nonpolar molecule is introduced, it disrupts this network. The water molecules have to arrange themselves into more ordered, cage-like structure around the nonpolar celli to maximize their own hydrogen bonding. This cage structure represents a decrease in the water's entropy, more order.
Ah, so if the nonpolar molecules cluster together.
They minimize the total nonpolar surface area exposed to the water. This releases many of those highly ordered water molecules from the cages back into the bulk solvent, where they have more freedom, more disorder. The increase in the entropy of the water provides a large, favorable thermodynamic driving force for the nonpolar groups to associate.
So the hydrophobic effect is really about water wanting to maximize its own entropy.
Exactly. And this effect drives the formation of structures like micelles and bilayers. Molecules that have both a hydrophobic part, like a long hydrocarbon tail, and a hydrophilic part, like a charged head group, are called amphipathic or amphiphilic.
Like soaps or lipids.
Yes. Below a certain concentration, they might just dissolve as individual molecules. But above the critical micelle concentration, CMC, it becomes entropically favorable for them to aggregate. If the hydrophobic tails aren't too bulky, they often form spherical micelles, with the tails hidden inside and the heads facing the water.
And if the tails are bulky, like phospholipids and cell membranes.
Then packing into a sphere becomes difficult. Instead, they tend to form planar bilayers, two layers of molecules with tails facing inward, creating a hydrophobic core and heads facing the water on both sides. These bilayers can close up on themselves to form vesicles, which are essentially the structural basis of biological membranes.
And these aren't static structures.
Not at all, especially at physiological temperatures. The lipid molecules within a bilayer are highly mobile, constantly moving laterally. They behave like two-dimensional liquid crystals. It perfectly illustrates how these fundamental molecular interactions, dipoles, van der Waals, hydrogen bonds, hydrophobic effect, lead to dynamic, functional structures essential for life.
It really ties everything together. We've gone from single molecule electric fields all the way to cell membranes, 5 huge topics, but all stemming from how charge and polarizability dictate the way matter organizes itself.
Absolutely. Whether it's explaining why a liquid has surface tension, why a polymer stretches, or how a protein folds, it ultimately comes back to these fundamental electrostatic interactions and entropic effects. That 1/66 potential, the hydrogen bond, the entropy of water. These are the rules of the game at the nanoscale.
And tracing something as complex as, say, the stability of paint or the shape of DNA back to those relatively simple principles, that really is the power of physical chemistry. It gives you that aha moment.
It really does.
Okay, before we wrap up, time for the final provocative thought.
All right. Consider water again. We talked about hydrogen bonds being strong, about 20 kJ/mol. Liquid water has a dynamic network where each molecule makes, on average, maybe slightly less than 4 hydrogen bonds, constantly breaking and reforming incredibly fast. Think about the collective energy tied up in that network and the dynamic balance required to maintain water as a liquid over such a wide temperature range compared to similar hydrides like H2S, which are gases.
So the sheer density and strength of that H-bond network in water
Is what gives water its uniquely high boiling point, high heat capacity, its surface tension, its properties as a solvent. This one specific directional intermolecular force, repeated billions of times, essentially dictates the properties of the medium in which life as we know it evolved. How different would everything be if that bond were just a little weaker or less directional?
A lot to think about there. The profound impact of one type of molecular handshake. That's all the time we have for this deep dive. Until next time, keep connecting those concepts.